All right, this is part two of a two-part series on convergence testing. The major focus here is to illustrate how IB might manage to craft a problem for paper 3 in the calculus option. They can craft a problem that will assess a variety of different understandings related to convergence testing. So in the previous video, we explored and concluded that this series, shown up in the upper left-hand corner, will converge if A is bigger than 1. And that is going to be the key to handling these alternating series that are very similar in nature. So I'm going to explore a couple of things, but first I'm going to jump to the conclusion right away. We're supposed to determine whether these converge or diverge and whether or not the convergence is conditional or absolute. So I will tell you that both of these series, alternating series, do in fact converge, but the first one converges conditionally and the second one converges absolutely. As a reminder, the concepts of conditional and absolute convergence are covered in more detail in another video you can find on the Haiku page or on my channel. So, what I'm going to do is tackle the second one first, because what I see built in here is squared, that is to say the A value from part A on this problem is bigger than 1, which means if this were not an alternating series, that this is going to converge. That's what we proved in part 1. So this is going to be the easiest one to prove convergence for. So here's what we're going to do. We're going to use the absolute convergence test. Basically, the way it works is if I'm sorry, I just lost my train of thought. Bear with me. Basically, we're going to take the absolute value of this particular series, and if we can show that the absolute value of this series converges, then the alternating series is absolutely convergent. So it's a nice, easy job to do. Basically, so we're going to go from k equals 2 to infinity, and the absolute value of this alternating series, and then we'll observe that if you take the absolute value of an alternating series, it no longer alternates. It no longer goes between 1 and or positive and negative. So all we have to do is ask ourselves, does the positive variation of a non-alternating variation of this series converge? Based on what we learned in part A, it does. Because A is 2, which is bigger than 1, which means we have a convergent series. And therefore, according to this test, the series converges absolutely. So the idea is, since this converges, then we know the alternating series is going to converge as well. Now, back to the other one. It's conditionally convergent as opposed to absolutely convergent. Now, here's why. The first thing we have to do is revisit the alternating series test. It has two criteria. The first is we have to make sure that for sufficiently large k, which in this case is for all of the k values 2 or greater, that the next consecutive term in this sequence is always smaller than the term before it as far as absolute value is concerned. So here's how we pass that test. First of all, notice that I already took the absolute value of the series for k plus 1, and I took the absolute value for k, which basically takes care of the alternation between 1 and negative 1. Once I take the absolute value, it's 1 in both cases. Now, it should be clear that this ratio is smaller than this ratio for the following reason, that since k is bigger than 2, we know that k times the natural log of k will always be smaller than k plus 1 times the natural log of k plus 1, just basic multiplication facts. We get to the second part of the alternating series test, and it simply says, look, does the sequence approach 0? If the sequence approaches 0, and we already proved this first condition, then the alternating series test says you have a convergent series. This does, in fact, approach 0. Therefore, the alternating series test shows convergence. However, because I'll actually write it out and then talk about it. If I look at the absolute value of this particular series, it becomes the series that we looked at or explored in part A, where A equals 1, which gives you a divergent series. So, since the absolute value of my alternating series is divergent, but the alternating series itself is convergent, we claim conditional convergence. It's only convergent when alternating. It's not convergent when not alternating. That's what conditional convergence means in a nutshell. So thanks for watching and being patient with my stammering. I hope you find this helpful. If not, rewind it and play it in slow motion. Thanks for listening.